Thank you. Yeah, you can tell I've earned my gray hair doing software quality, software engineering for a number of years. Topic for today is the myth, or some myths behind the software metrics. Some years ago at PNSQC presented a paper on the darker side of software metrics. This is, in a way, a follow-up, but I want to talk about some of the things people think about software metrics that just aren't really true, and why those things tend to be myths, and also want to talk about some things we can do that are positive uses of metrics. The good news is, with Caper's presentation this morning, I'm not going to directly contradict much of what he said. And I wholeheartedly agreed with a lot of what he said. So anyway, so myths, legends, explain some practice or idea. Superstitions, I'm not going to go into detail about, but these are beliefs or practices from ignorance or trust. In our business, people do things because Myers wrote that we ought to do it in 1978, and of course, we ought to do it. So yeah, everybody does that, right? Everybody understands that. Not necessarily. And in metrics, this is particularly interesting. Superstitions remain unchallenged until somebody stands up and says, wait a minute. And so for a couple of things, I'm going to say, wait a minute. I don't look down. Okay, remember that. Yeah, and one of the things I kind of rail against is taking things out of context. Yeah, it's like taking things in moderation. If you look at, well, I tend not necessarily to do that, but practice what I preach, not what I do. But applying it out of context, many of these metrics are really useful sometimes. The difficulty I have is that many of these metrics are taken as universal truths, and that isn't the case, and that can be very damaging. So the myths that I want to talk about: measurement is easy. We kind of trivialize that. We'll count the bugs. Okay, cool. I'll talk about that. If we measure it, we can control it. Yeah, sure. No, that's not true. Measuring something doesn't change anything else. We're just taking observations. Nothing's going to change. Sure. We're measuring things humans are involved with. The arithmetic makes sense. So we look at bug density, right? Everybody knows what that means, right? And the arithmetic really makes sense, yeah? Precise and accurate measures make them valid. So we have an exact count. 47 red cars. Divide that by the number of yellow cars, and yeah, we can come up with 6 decimal places of accuracy. The metrics reflect the attributes. There's something that should go along with metrics called models that relate what we are measuring to what we want to know. talk about that. And I'll make the claim that the commonly used metrics are not necessarily valid, not necessarily useful. Some of the terms I'll use, I may not use all of them. Entity, that's the thing we're trying to describe. So the entity may be defect density. We're trying to describe that. Attribute, the property that we're trying to measure. So that's the value that we're trying to figure out. The measurement is the assigning of the value. The measure is whatever number we came up with. Right? Reliability is the repeatability of the measurement. If we take the measurement again, do we get the same amount of time, or is it possibly different? And if so, is it different by a factor of 3 or by 6%? Okay, so to the degree it's repeatable, it's reliable. Validity, freedom from bias. I mentioned before about humans being involved. Yeah. Measurement error is the variation. As I mentioned, time. Right? If we're measuring time, there's some natural variation that's going to happen. Our stopwatch isn't necessarily that good. And then the model, I'll go into quite a bit more, but it's relating the measures to the entity. So we're trying to learn something in our metrics. We're trying to describe something in our metrics. And the model relates what we're measuring to what we're trying to find out. Does this all make sense at this point? I haven't gotten into the fun stuff yet. So the measurement is the observation, is a value that we're deriving. And the metric is some arithmetic or mathematical function that's applied to one or more measures, actually generally applied to multiple measures. Boy, that didn't get translated as it moved from PC to Mac. So, an example of a metric. Transaction rate is the transaction count divided by the time interval. Right? So the number of transactions and the time are measures, and the metric is a rate. Straightforward. First myth, measurement is easy. No. What are we really measuring? I mentioned bug count. Is that bugs before they've been confirmed, or only ones that have been assigned? Does that include the bugs that have been deferred? Are we actually counting total number of bugs, including those that have been closed? Are we including duplicates? Are we recalculating when bugs are defined as duplicates, or ones that have been assigned are found to be not a bug? Yeah. So, yeah, we're measuring bug counts, and that's something you can get directly from the database. But is that really the number of bugs that have been encountered? I don't think so. Our standard of measurement. Do we have a yardstick? Time. Wonderful example, right? How fast is your processor? What tasks are running in the background? What resources such as network bandwidth, are shared, and therefore you're competing for the, so time. If I run in a processor that's twice as fast, or I run in a system that's got 1 gigabyte versus a system that's got 8 gigabytes of memory, real memory, does it make a difference? Is time actually a constant? How many hours of use? Right? Capers mentioned number of users over the 90 days. Now, is that number of users running the program full time, or the number of users that have looked at it? So time is not necessarily a constant. How accurate is your measurement? Lots of reasons that we may not be accurately measuring things. Capers mentioned function points and lines of code. I was quite surprised. Is Capers here? Okay. Now, I would invite him to, I would invite him to respond. So it's not that I'm going to say anything I think would embarrass him. So, yeah. Accuracy. Function points. He said that 110 Fortran statements was a function point. Okay, that means I don't need to compute function points if I have Fortran, because I can just take the number of lines and divide by 110. So why am I computing function points? How accurate is that? Well, it's the average over the 4,000 programs that we have checked. Okay, so what's the variation? How accurate is that? How repeatable is the measurement? I talked about time. You're going to get variation, natural variation in the measurement there. Even if you run the same system, same configuration, same backgrounds, clear network, you won't get the same amount of time because there's natural variation. Yeah. And program size, Capers talked about function points, which is a reasonable mechanism for being able to compare some attribute about software between two different kinds of programs, two different programming languages. I'm not sure that we're measuring size, but we're measuring some attribute that kind of sort of surrogate for size, which we really don't understand what the size of a program means. So we really don't understand what attribute we're looking for. But that, measurement is easy. Right? As I just mentioned, program size. Do we really understand what that is? Complexity. Do we know what that is? I don't think so. And so trying to describe metrics, trying to figure out metrics to describe an attribute we don't understand, that's kind of silly, I think. And is this something that we can directly measure? If 110 Fortran lines equals a function point, then we can probably directly measure it. However, I can cite an example where I'm working at an organization where the management saw that the defect density was too high. And so management in their infinite wisdom, proclaimed that the defect density needed to be reduced by half quickly. And within 2 weeks, they had actually reduced the defect density by half. How do you think they did it? They doubled the size of the code base. Right? They literally, for 2 weeks, what they did was they figured out how to break the code down to reduce the metric, right? Without, well, actually, they probably put a bunch of bugs in, but you know, yeah. Can it be measured directly? Is it repeatable? And what amount of variation should we expect? Again, what amount of variation do we expect if we're taking timing on different systems to compare? With different memories, different times of drives, different connectivity, different background activities. Yeah. What kind of variation do we expect? Factor of 3, factor of 5, factor of 10. And so how accurate are those measurements? How useful are they really? Second myth. So if we measure it, we can control it. Sure we can. Measuring something means we have some information. Whether it's useful information, good information, valuable, we have some information. It may be poor, it may be good, and oftentimes, when I talk about models, I'll elaborate. It may or may not relate to what it is we really want to know. We use a lot of surrogate measures, and we, you know, yeah. Anyway, Tom DeMarco in 1982 wrote, "You can't control what you don't measure." Now, I misinterpreted some things he said much later. I talked with Tom, and based on his IEEE software article, he's, you know, the best quote I could find was, "I've become increasingly uncomfortable with it." In other words, the statement that you can't control what you can't measure, there are a whole bunch of things you can't measure. You know, the enthusiasm, amount of experience, the commitment, you know, those are intangibles in a lot of ways. You can't measure them. Can you control them? You can influence them. Particularly if you think about it, you can negatively influence them a whole lot. Right? So if you can negatively influence something, you probably can positively influence it. But you, as I'll talk about in a bit, watch out for side effects. There always are going to be side effects, and so anyway. But what Tom has revised the thought is that if you measure something, maybe you can influence it in ways that you want to influence it. Can you control it in software? Probably not. Thus the issue of doubling the code base in order to have the defect density. When we take measures, when we compute metrics, two ways that they get applied. And I was having a discussion last night and another one this morning with people about observation versus control. When you use measures to observe, retrospectively, for example, you can learn a lot. You can learn very valuable information. You may actually have actionable information. But if you try to use it to control, my experience has been 100% of the time, you get unanticipated side effects. And 95% of the time, maybe 99% of the time, I'm guessing, metrics, right? It's dysfunctional. That the effect is not helpful to quality, to efforts. So the observation versus control, what do we do with that information? Who do we give it to? Personal metrics is something I'm actually an advocate for. And by personal metrics, I mean that the person who is generating the information is the one who gets the information. And they can act on it or not. If it's distributed beyond there, people will often interpret it as judgment. And as soon as they feel somebody else is drawing conclusions about their information, it'll get distorted. And so it's not even useful to them. But the PSP, Watts-Humphrey's ideas that we should be writing down, I don't do this, but Watts does, writing down all of our mistakes and categorizing them, analyzing them so that we can improve. Well, okay, metrics, observational metrics or personal metrics. Yeah, if we want to improve, knowing better the classes of errors we've made, the kinds of things we repeat, okay, very, very helpful. The modules that we are working in that tend to have more bugs than others can be very helpful. But only if I have that information. If my boss has that information, I may double the code base. Yeah. The density's lower now. And the thought is, and often is true, just because the measures are being taken, you're going to change behaviors. Not necessarily for the better, but you're going to change behaviors because you want to see better numbers. And software development, software quality is a human process. It's a social process. It's not a technical process. There's technical elements to programming, but ultimately it's a social activity. And so we're dealing with human responses when metrics are being taken. Side effects. I'll come back and talk a lot more about models in a bit. But without a mechanism that describes the relationship between the attribute, the information we want to know, defect density, better example, programmatic complexity. Right? We want to know what the complexity is. What model tells us that when you create a flow graph of your program, there's a relationship between the number of nodes and the number of edges that describes complexity? What model do we have that says that is related to complexity? You know, it's an interesting number, and it can be computed, but what does it mean? And does it have any relationship to the attribute that we want to know about? I think the answers are the attribute itself, yeah, reliability of software, stress on software. These are terms that people commonly use, but I don't think in the computer science sense we have any idea what they are. Now, the size of a program. Is it the footprint? Is it the weight, the number of lines, number of function points, number of things it does? I don't know. And so when we try to describe an attribute that's not defined, we're starting out at a major deficit. Now, I'll get into it later. Measures and metrics can be very useful. In large part, it can be useful if you understand that it's a surrogate. It represents something we might like to know about, but we can't figure out what it is, so we'll substitute this other. And kind of sort of know something somewhat similar to the attribute we think we need to understand about. Very indirect, but you're absolutely right. I can't describe those concepts to you. I can describe what I feel, you know, the size of a program means. I like weight. Yeah, but volume of a program. We're talking defect density. What is the volume? Yeah. Yeah, and anyone here doing computations like MTTF, mean time to fail? Okay. Keith, I saw your hand. CPU speed factored in? Okay, so you're computing an MTTF for a specific environment platform. Okay. Okay. So do you think that's generalizable information? Applicable in the wild? Okay, so you see a correlation between the computed MTTF and the observed MTTF in the field, in the wild. Okay, the correlation. Yeah. Okay. As I said, some metrics are useful. The thing I've seen with people doing MTTF is trying to compare one release to the next, and they use different generations of equipment, different configurations of equipment. Okay, you may have a measure of MTTF on this new equipment, but it has no direct relationship, maybe not even an indirect relationship with the other measures. And so to figure out, has the quality improved or gotten worse? The answer is yes. It's improved or gotten worse, and it has nothing to do with the MTTF you've computed. It has a lot to do with the configuration. Mm-hmm. Right, so you do OFAT and one factor at a time, and by comparing what changes with that, you can kind of, sort of relate the one environment with the other. Okay, sort of, kind of. I can think of a bunch of other secondary factors like background processes that might be involved, but excellent approach to mitigating. So somebody else had raised their hand about MTTF. So my question is, how do you deal with things like okay, so okay. Okay, so the keeping the environment the same, and if there are changes, one change at a time. Yeah. So yeah, issues outside your control. In this talk, I'm not going to go into the model that I present in the automation talks, but there are many influences on the behavior of the software under test, many of which we don't have direct control over, like network availability, and what background processes are going on, competition for resources. And so, yeah, lots of influences going on that make it hard to repeat tests. I contend that if you rerun a test, it is not the same as the first time, no matter how much you try to control. And that model that I have explains why. So another side effect of measurement, I have observed that when people make estimates, particularly when they're estimating several measures, they've already figured out what the answer is, and they're backing into what the numbers ought to be in order to prove their point. This module needs to be worked on, and so the expectation of failure is high, the impact is very high. Okay, they've already drawn the conclusion that that module needs to be checked more thoroughly. Why don't we just say that? Why do we need to generate metrics using estimates to? Estimates, that's a seat of the pants number that kind of, sort of, maybe represents a value that might be close to what we're trying to measure. At the same time, I'll go to a developer for an estimate on when they're going to finish some work. It's an estimate. It's a guess. Kind of, sort of like what I'd like to know. I don't go to management and ask that question because they always are optimistic. But go to the person doing the work, and you might get a reasonable answer. And I find that numbers, I'll talk a bit more about accuracy, but yeah, people will take the measure of time, right? If I'm doing a computation on transaction rate, so the time is right? And I count the number of transactions and measure the time, and bingo, I've got it to 5 decimal places. Well, you know, kind of, sort of, to the nearest 10 or 100, but it's, yeah, take the measurement again. Yeah, the time changes, the number of transactions changes. And people optimize what's tracked. We're all familiar with the Dilbert cartoon, where management, the pointy-haired boss says, I'm going to pay a bonus for bugs you fix. And Wally's response is, oh, great, I'm going to build me a minivan this afternoon. You know? If you're rewarding somebody for fixing bugs, what's their incentive for not putting them in? Particularly if the developer's being incented to fix them, they know what bugs they put in, and so it's straightforward to do that. And I already gave you the example from DAC of the. What was really funny about the doubling of the code base, I bit my tongue because management demanded that we reduce the defect density, and I didn't believe in doing that. So I didn't say what I thought to management when they said, fantastic, see what we can do with metrics? Yeah. They got kidneys. Human behavior I've been talking about. And it's interesting, in my darker side paper and talk, I describe organizations where they have higher costs, lower quality because of their metrics programs. And in most of those instances, they were totally unaware that they thought they had wonderful metrics programs. But the human behavior was sometimes bizarre, often subconscious. But yeah. Right? And unreasonable expectation. I mean, in the case of DAC, in case of doubling the code base, there was totally unreasonable expectation. So I kind of expected that kind of response. I didn't expect that much that fast. I figured they would at least mask it over time. You know, let it take a couple of months to improve. You know, improve one module at a time. No. They decided that they were just going to, you know, get this past them and, you know, move on, start doing real work again. So, okay. Bug model, bug find rate. Yeah, you've seen the curve of what the expected rate of bug find. I've got it coming up again later. I'll tell the story now. Had an associate who was co-teaching CSQA preparation, our CSQE preparation, certified software quality engineer from ASQ. And we were teaching the class in Silicon Valley to prepare people to take the exam. And he had used the bug find rate curve on a project at Xerox, and was very proud to tell me that for an 18-month project, they hit that curve every week for 18 months. Right? Now, in my college days, we called that dry labbing, and you got an F. Right? How could you possibly get exactly the predicted number of bugs every... People go on vacation. Hey, this was a 2-day week because we had Thanksgiving. We had this week off because it was between Christmas and New Year's. Right? But they got the right number of bugs that week. So the only imaginable way is on Friday afternoon, if I don't have the right number of bugs, let me go look at the help files. Find some more bugs, right? Or I suspect in their case, let me write some duplicates really quickly because they won't clear it up until midway through next week, and then yeah, I will have met the number. Oh, I hit my numbers on Wednesday afternoon. Where's my yellow stickies? I'm going to finish next week. 18 months, and it never occurred to him that there was something odd about that. We predicted when the bugs were going to be found, and we found them. And in terms of human behavior, it's the expectation of the use of the metrics. Right? If I'm providing numbers and I think management expects to see some particular values, I'm going to work to give them those values, whether they actually have that expectation or desire or not. So it's my perception of what they're going to do with it. It's my perception of what... So honestly, they may not be trying to figure out who's the best tester based on the number of bugs reported, but if I think that's the case, I'm going to report a whole lot of bugs. I'm not going to help the developers to improve the quality. I'm not going to suggest that they have this systematic error that they're injecting every place, because I can find all those. That's cool. Right? I can increase my bug count. Aberrant behavior. Anybody have counterexamples or experiences about the people responding to measures, metrics? No? I have, yeah. Okay, so you have an SLA, service level agreement, with a vendor to you of software, and the metrics that are specified are met, and anything else is fair game. Heaven only knows what you're going to get with other characteristics. Yeah. I mean, to me, that's expected behavior. Sure. And to the pointy-haired boss, oh no, we need to add these additional metrics. Yeah. So add those additional metrics. They'll find other places to not do the work, and that. Yeah. So in mathematics, how many people are familiar with the types of numbers or nominal, ordinal, interval, and ratio values? Okay, let me take a couple of minutes here. 4 basic categories that we can classify things into. Nominal are things that are just categories. Airplanes, fruits, right? The color. It's a category. And we can look at things in that category. We can look at sets. We can count things in that category, maybe. But the category itself is nominal. Right? You don't divide yellow by red. Particularly, you don't divide oranges by rocks. Those are nominal categories. We put things in. Ordinal means there's some ranking. Now, I was first in the race. You were second. You were third. So there's an order there. But that's all we know is the order. We don't know how long between first and second and third. Bug severity is ordinal. There's an order to it. Sometimes. Yeah. Then you get the category which is E. Enhancement requests, which is not ordinal. It's just different. But ignore that. Interval. Interval data, like temperature scales. Right? The difference between one value and the next, the interval there, between 72 degrees and 75 degrees, is the same as the interval between 45 and 48. Right? So we can look at these ordinal values, interval values, and differences, for example, make sense. But you don't divide 72 degrees by 45 degrees because the ratio doesn't make logical sense. Ratio numbers are proportional. That means that there's a zero. And ratios, the number of bugs in severity 1 and the number of bugs in severity 2. Now, the severity 1 and 2 are categories that are ordinal. The count of bugs in those categories is ratio, because we can have 0 bugs in one of those categories. So we can say that there are twice as many severity 1 bugs as severity 2. Hopefully the other way around, but you should get the point, right? We can do ratio computations. Okay? So, nominal scale, we're done in terms of mathematics. Yes? Yes. The deal there is that if it's a ratio value, it is also interval. If it's ratio, it is ordinal. So ratio values encompass everything. Interval values are also ordinal, right? Because 75 versus 78 degrees, there's an order there. Subtraction makes sense. With ordinal values, right? And yeah. So the reason I bring this up is that, for example, ordinal values. I came in first, you came in second. You came in first, I came in second. Does that mean you're twice as fast? Yeah, are you 3 times as fast as the person who came in third? Yeah. We're doing bogus arithmetic. Because if we're dealing with ordinal values, we don't know if the amount of time between the person coming in first and second is the same or different from the amount of time from second to third. And certainly ratios make no sense. All we know is this event happened, that event happened, that event happened. There's an order to this universe, but that's really all. So does that explain about the concentric circles? Thanks. Nominal values, arithmetic makes no sense. Don't add orange to red. Now, on a color scale, yeah, maybe, but it also depends on whether you're looking at gels and light versus darker colors. Anyway, mixing colors. Ordinal, they're ordered categories. So most math on ordinal values doesn't really make sense. You can identify the middle element in an order, right? There were 47 people who ran the race. The 23rd was the middle one. Or halfway between the 23rd and 24th. Yeah. You can't do ratio sums differences. We don't have an average severity 2.5. Yeah. Again, the categories for nominal and ordinal may have countable things in them. Right? We may have some number of oranges. That's not, the number is not nominal, but the category is nominal. Interval, calendars, thermometers. The interval of time from project beginning to end between milestones, you can shift that by 6 months, and the intervals are comparable. Right? But you can't divide it. Right? So differences make sense. Ratios don't make sense. And ratio data, hey, the cuffs are off, the walls are missing. You can do mathematics with ratio data. Thus we have the Kelvin scale of temperature, which has a 0. So you can do ratios. 0 is really cold, but questions about the kinds of arithmetic? The reason I bring this up is when you look at metrics, there are times in which interval data is used as ratio. Let me see if I can. Okay. This is a Macintosh. So that's not going to work. I can't look at my notes. don't come up with one off the top of my head. So I won't. Okay. The math, think about it. When you are expected to look at ratios, differences, does it make sense? The difference between severity 1 and severity 2 is not the same as the difference between severity 2 and severity 3. The example, FMEA, that's the failure modes and effects analysis, is a arithmetic model that starts with estimates, which makes it kind of interesting to begin with. But you estimate the chance of, or a scale of 1 to 10, of severity, of impact, likelihood, visibility possibly. And then you multiply the things to come up with this risk value. Ignoring the fact that they're estimates, those are ordinal values. Multiplying them arithmetically makes no sense. And so the engineers who use that technique sometimes know that it's bogus arithmetic, and therefore look at the answers with a grain of salt. They may or may not be useful. They may or may not be indications that we might think about taking action. The regulators who look at those take them very seriously. So in an FDA environment, you do the FMEAs because they are required. And if you are below 50, you don't have to do anything. If you're above 50, you must take action. My experience has been, if it's 55 and people really don't think action should be taken, oh, well, we misestimated that value, and oh, it's 45 now. Silly me. But anyway, so yeah, there was an example of misuse of the arithmetic. 42. Some people laugh, right? It's the answer to the question of life, the universe, and everything. The only difficulty is that the real question has been forgotten. And so 42 is the answer, but we don't know what it's the answer for. Yeah. I think I've hit the other points already. Yeah. Am I making everybody feel really good about their metrics programs? Okay, I will get there. I will get there. In the second half, precise and accurate. Boy, that probably sounds really awful to the recording. So precision is about the number of significant digits. 4 versus 4.0, 4.00. So precision is indicated by the numbers that we put in. If you have an answer of 400 versus 400.0, fairly significant difference in the expectation about the precision. 400 may be plus or minus 50. 400.0 implied plus or minus 0.5. accuracy is having the right value. So accuracy is about the time. Do we have an accurate measure of time? And in the cases that people brought up, they try to maintain factors so that time is relative to itself, right? Relative to that configuration, and so is relatively accurate. There's some variation there, of course. Estimates are approximations. These are guesses, right? Accuracy of an estimation is poor because it's a guess, right? So I guess it's going to take 10.345 hours to code this. Yeah. Either you have it coded and you're sandbagging for all that time, or you're being really silly. 10 hours. Okay, that may be, plus or minus 5 hours. Right? Small enough. We may get by with that. 243 hours? Huh? That's an estimate? Yeah, you computed it. Let's see. This year, I want to spend 4 months working on that, and that's so many hours per year, and surrogate measures. How many people know what surrogate measures are? Okay. Very few. Okay. A surrogate measure is a measure we take of something that we can measure because we can measure it instead of the thing we really want to measure. Let's see. What example did I come up with surrogates? No. Keith, off the top of your head, surrogate measure. Example. Okay. So, okay. Skin color and body temperature. So you take a look at the color of the skin in order to figure out a person's temperature. Okay. Why are you looking at the color? Because you don't have access to the person to measure their temperature. How accurate is that surrogate? Given body types, I would think it's not very accurate at all. But if that's the only thing, you've got a photograph, it's the only thing you got. Actually in the airports, in the Middle East and Philippines, at the customs, they have infrared cameras in order to tell if people have fevers, because they don't want sick people coming into the country. But they use infrared. They don't use shading color. Right. So surrogate measure is a measure of something that you can get instead of what you really want to know. Yep, and an estimate of the number based on that. Yeah. So, yeah, because it's a surrogate measure, it's neither precise nor accurate. It kind of sort of maybe tells us a little bit about the thing that we want to know about, but it doesn't give us a precise, accurate measurement. And I find it funny because we'll compute defect density to 4 decimal places. Okay. Even to 1 decimal place. 110 lines of Fortran code is a function point, so if I create another 55 lines of Fortran code, I could get that from 0.7 to 0.45. And of course it's accurate, because we got 2 digits after the decimal place. Oh, okay. I didn't need that one. Using estimates. Yeah. So when we have estimates, when we have wide variation in values, non-repeatable measures, using arithmetic compounds that variation, compounds the difference between what it is we're trying to learn and what we are finding arithmetically. And often, skin color, number of defects found. They're based on surrogate measures, and the technical support costs based on number of defects. Well, it turns out that the bug that was first found in the field was it doesn't install. The support team, based on the fact that there was only going to be 1 bug, was 1 person, and the company is huge soft, and they put out 100 million copies the first day. They are going to get a couple of phone calls. They may have been accurate about their estimate of the number of bugs, but they wouldn't be very accurate about the support costs. They probably would not be accurate about the marketing costs, or their goodwill, or their stock price. But anyway, yeah. Okay, estimates are always poor because they are necessarily guesses. And so how accurate is that guess? Right? Right? Okay. Okay, but there are a huge number of factors, hepatitis being one factor. If you've made an estimate for a team, then you're able to average, and the accuracy of that estimate may be better, would be better probably, than an estimate for 20 days for 1 person. Because if that 1 person gets sick for a day, that's likely to impact it. In my experience, a gut feel of an experienced person is more accurate than the computations. And so if you have a team of 20 and you are doing the estimation based on your decade or so of experience, or 2 or 3, you're probably pretty accurate. But if it's a brand new team to me, even having experience, my estimate is likely to be fairly poor. It's going to be derived from queries with my people, but I don't know how well to trust them. I don't know how good they are at estimating. So there may be cases in which you get it. Readiness for release is a wonderful metric I've seen. And what I prefer to any 42 is the tester's gut feel. Go to the primary tester and ask, is it ready? If their answer is no, then I ask, why? Or why not? Show me examples. And if they can't show me examples, okay, we may be in trouble, but I'm not going to be able to convince management to hold up the release. Chances are excellent. If it's somebody with experience, they can give me an example or two of why it's not ready for release, and their gut feel. I ask them to back it up. And oftentimes, most of the time, I'll get anecdotal evidence that I can present to management so they can make a good business decision. Is it really ready for release or not? That's not my call, by the way. Accuracy. So, good challenge, but I still hold by its poor. So, metrics models. Alluded to this a couple of times. Right? A model describes a relationship between some real world thing, attribute, and some measures or metrics or some possibly useful way of simplifying the world. Most models are approximations. You may use surrogate measures. Without a rational model, metrics are meaningless. And a rational model, I mean one that you might look at, I might look at, and say, okay, kind of sort of makes sense. Okay. Most models are approximations. And if you add bogus arithmetic to a questionable model, you get, I would say, interesting results, but most of the time they're not interesting unless somebody uses them. And then it's that they use them that becomes really interesting. The metrics themselves, no. So here we have two models. Right? One of them actually flies, and the other one is a ruler on a loaf of bread. One is more accurate than the other. So some models are better to some degree. And there's a fair degree of difference between the accuracy of these models. For some purposes, if your purpose is to teach a small child what the outline of an airplane is, do you need to go to the trouble of creating that complex model? No. No. The loaf of bread with a ruler is probably adequate for that purpose. Now, if I'm trying to put it in a wind tunnel, well, actually, that one's probably not accurate enough. But yeah. The ruler with a loaf of bread, even if you shove the ruler through the loaf of bread in a wind tunnel, it probably isn't going to be a very good model. Particularly if it's fresh bread, because, yeah. And quoting George Box, all models are wrong, some are useful. So the metrics models we're using, they're models. Some are useful. Right? That's the good news. For some purpose, to some degree. So, I want to talk about two fairly common metrics. How many people in your organizations compute the defect density? No hands. I have intimidated everybody. How about the bug find rate? Okay, okay, several people. So I've already talked about the question of what does it mean to have a bug density? And what does it tell us? What is the attribute we're trying to find out about with bug density? The bugginess of our code? Oh, what readiness for shipment? Okay, so yeah. And so with both the find rate and with the bug density, I've seen them used for predicting when we're ready to ship. In the case of the bug density, we have the DAC question, which basically you can increase the number of lines of code and therefore be ready to ship. And the bug find rate, when the bug find rate falls far enough, then cool, it's ready. Two things about that I found. One is when the bug find rate goes over the top of the curve, it's generally because your tests have been exhausted. And if you do a different kind of testing, look for a different kind of bugs, it goes back up. And yeah. So if you change your focus, unless you're Rob with this 18-month project, then what you get is what you see, is how I describe that. Yeah. You see this, and that's what you get. Yeah. So the other thing I've seen with the bug find rate is a phenomena that actually, I'm told on good authority, I won't name names, either of the company or the instructor, but an associate of mine was teaching a class and was talking about bug find rate and readiness for release. And one of the testers in the class said, yeah, for a long time, we thought that the developers were showing real appreciation for us when they sent us off to the movies. They paid for us to go to the movies, which was terrific. We were working our butts off, and it was getting close to release, and the week they sent us 3 times to the movies, we figured out why we're not reporting bugs when we're at the movies. And the instructor asked, when's your next release? Friday of this week. And you're in a 3-day class. You're not going to the movies. but they were ready for release. True story. Secondhand, but nevertheless, I really trust the person who told the story and believe it from the company that he was teaching at. And as I mentioned before, how do you count the bugs? Oftentimes what I see is at some point the test group starts regressing tests. They go back to the ones that have been fixed. And so the likelihood of finding bugs goes, yeah. Mm-hmm. Right. And so every bug you discover, you fix. Okay, instantly. So, readiness for release, send the tester to the movies, and you can be ready real quick, right? Or give them an assignment to write up the results of what they just did, or tell them that they have to prepare for the next sprint. It's a matter of, look over here, look over here. Oh, yeah, it's shiny. It isn't always the case, right? But it's gameable and subconsciously gameable. Maybe systemic. It may be that the way in which things are organized, people start regressing the bugs, and therefore the bug find rate drops off dramatically because they're paying attention to things that aren't likely to find bugs. As I said in my darker side paper, many of the organizations had no realization, and even when I was done, didn't believe that the metrics were dysfunctional. They just, even after being shown, they couldn't accept it. So, number of bugs per unit time. Bug density, bug count divided by the size of programs, right? What's wrong with that computation? How did you count the bugs? How did you measure the size of the program? What are the variation in those? The size of the program may vary by 30%, depending on how you measure it. So take the size of the program minus 30%, and the size of the program plus 30%. And that gives you the range of bug density size. And now take the bug count and factor in how they're counting it. And I mentioned many of the ways they can be counted, right? But what are the factors they aren't including? So what's the variation on the bug count? And you take the two extremes, right? The largest denominator, smallest numerator, largest numerator, smallest denominator. And what you find is that the bug density is somewhere between 1/2x and 2.5x, right? Where x is the number you actually compute. Cool. So our bug density is between 0.5 and 2.5 bugs per KLOC. Helpful? Yeah. Okay. Okay. So the question is what to do about it. And when do I get to that point? 2 slides. And I've already told some stories about the bug find rate model. It's, yeah, what you get is what you see. Yeah, you see this, that's generally what's going to happen. Because people believe it. So for whatever reasons. Okay. Excuse me, it was a couple slides off. Common measures, vet typing, number of test cases, passing, failing. Oh, passing, failing is one of my fun ones. And percent completion is also a fun one. Let me briefly with passing and failing. Yeah. When a test passes, what's that mean? It means didn't fail. It means we didn't notice anything. Doesn't mean there's no bug there. It just means we didn't notice anything. And when a test fails, what's that mean? Did not meet the requirements? Didn't do what we expected? How about a person needs to look into this because chances are there may or may not be a problem here. Right? It may be expected behavior under the circumstances. The network timed out. The services weren't available. We don't know yet. Right? We need to. So pass doesn't mean pass, and fail doesn't mean fail. And yet I see these wonderful dashboards that you're making instant decisions based on pass and fail. Cool. Really? How good are your tests? Now, you may not have better surrogate measures, but there may be other ways than believing the percent completion of tests. This is wonderful because are all tests created equal? Yeah. No. And so your completion rate is based on the number of bugs you find, the length of the tests you run, the order in which you run the tests, how you measure completion. Is it the amount of time expected that you've run through, or is it the number of tests? And all tests aren't. Yeah. Anyway, So the questions I use with metrics, and after this we get to the fun part. If an attribute improves, if the bug density gets less dense, does the metric always reflect that? Okay. Is it possible that it improved and the metric got worse? What's the underlying model? Look at the arithmetic. How can it be distorted? Lines of code can be distorted. And what things can change the attribute without being reflected in the measure or metric? So the defect density may go up or down, but we don't see a change in the metric. Is that possible? And under what circumstances? Quite possible if you're not doing additional testing, because the bug count is the bug count. So, what can we do? First thing I try is discourage the use of bad measures and metrics. And bad measures and metrics, look at the previous slide. I look through those characteristics, and if I find 1 or two that are really bogus. I generally consider it a bad measure of metrics. Invent ones useful in your context. I go to management and I ask, you know, what is it you're trying to find out here? And what kind of information will tell you that? And, you know, forget about these IEEE standards and just what kind of information would tell you that? Oftentimes, metrics aren't the way. But by asking that question of management, we may derive some metric for this organization at this time, or better yet, a dashboard, you know, a number of measures, metrics, that taken together fill in a picture. You know, work hard to only use them for observation or give them to the people who generate them so that they can personally improve or not. Because if you make them public, if you use them for control, they are going to get distorted. Help people interpret the numbers. Particularly the pointy-haired managers need a lot of help here. Because they will misinterpret to the either best possible or worst possible, depending on their personality and the time of year and whether their bonus is coming up or, yeah. So help them to understand, and yourself understand that the reason management's getting this information is so they can make good decisions or better decisions. And to the degree this information can help them, let them know, and to the degree it may mislead them, help them to understand that that may be the case too. Yeah. Right. Why can't we use it? Because it's meaningless? Because it causes tremendous dysfunction in the organization? Because it doesn't really fit what we do? It may be that it's about as good as you're going to get. So, okay, use the standards. Yeah, I read the standards. I know about them. I use them when it makes sense. And often it makes more sense to use the standard because I can point to the standard than to invent something that's very similar, but I had to invent it. And if possible, only give aggregates to management. You know, 20 people on a project. You know, so if there's 20 people on a project, don't tell them what individuals are going to be doing. Give an estimate for the group. And if you have metrics, you know, identify or create ones that are useful, and the ones that aren't useful, discourage them. Use the metrics for observation, or create balanced scorecards. A balanced scorecard is where we have a number of measures and metrics that together tell a bigger picture. Yes? Some useful metrics. Yeah. Well, I have found that the measure of number of bugs in a module, okay, in a component, can be useful to the people who are managing or maintaining the components or inventing them. It's useful information, but giving it to management can be a big problem because they say, well, that's a lousy programmer because they got a lot of bugs. Well, your best programmer is the one you gave the gnarliest problem to. Right? They inherited that very buggy module. the hardware characteristics have changed, and therefore what was working yesterday ain't working today. Lots of reasons that that could be bug prone, other than incompetence. So if you provide that information to the person who would act upon it, the tester or the developer, they can work together to decide, is action appropriate and what actions might be appropriate. Okay, so that's an example of a metric that I've put in place. I should have prefaced this whole thing with, I'm a reformed metrics advocate. I used to put metrics programs in place. And over the years, I've seen too much damage done by people misusing, misinterpreting, and in the early days, believing the metrics because I believed them, and then figured out that, yeah, my experience at DAC was one of the points that I went, huh? You know, the cyclomatic complexity was another issue at that organization. If it was too complex, they wanted it uncomplexed. And a case statement is totally complex. You can increase the complexity from 3 to 43 with one statement. And to make it less complex, you end up making a tree of conditionals. Huge spaghetti code solution, but it gets the complexity down. Realize that the measures and metrics trigger questions. They don't give you answers. They will tell you that this is something that might be investigated. Same as a failure on a test. It's an indication that somebody ought to look into this. But it's not an indication there's a problem. Communicate the validity and avoid the direct application for project control. Direct application meaning the pointy-haired boss is going to hire more people or reassign people or come pound on the desk or give people a bonus. And that's it. 1:47. I'm 1 minute before. I will stick around for a while. We have a break now. And I'll answer questions. You guys have been a great audience. It was fun for me. I learned some stuff.